Good morning and welcome to today's computer vision lecture. Last week, you had a chance to pick a robot if you want one for your computer vision project, and hope you had some time to set up the robots and test them. And this week, we will continue with the content of the lecture. 2 weeks ago, we looked into regions of images and segmentation. We first of all looked at what segmentation is, looked at some simple segmentation that we could do, like a binarization, and looked at more complex segmentation issues. We looked at psychology, in particular, Gestalt theory, to maybe get some ideas about how we can do segmentation in terms of rules. And we saw more complex segmentation approaches, like starting with histograms and quadtrees, and then we looked in detail in k-means, which is an unsupervised algorithm that does clustering for us. And we discussed it first of all in general, and then we also applied it to a image processing problem, concretely for compressing images. After that, we continued with feature detection and looked into more complex features, in particular the Hough transform and the Harris corner detector. We initially briefly discussed ransack, which is a generic feature or a generic algorithm for finding parameters in a model when there's noise, and we saw we can apply this to computer vision and feature detection. And then in greater detail, we looked into the Hough transform, which allows us to find straight lines in an image. For this, we had this very good visualization to see all of this step by step. The only issue is running the Hough transform is computationally quite heavy, and that's why there are also various alternatives to this. Then we also wondered about corners, which are very distinct features in an image. And for this, we derived the Harris corner detector, which was quite a few steps and required quite some maths. We needed for this the Taylor expansion, for which we did a quick revision. And then once we had done this matrix vector decomposition of our error or change that we computed, we wanted to get the eigenvectors and in particular the eigenvalues of matrix M. And for this, we did a quick revision of eigenvalues and eigenvectors, and we got the eigenvalues and saw what they actually mean in the image and why they're distinctive. However, calculating the corner response that way is computationally heavy, and that's why there's often an alternative which gives us an approximate result. And for this, we don't need to calculate the eigenvalues. Then we saw there are obviously many more feature detectors, and that's a huge topic in computer vision. And in practice, for some vision problem, you just don't know which feature detector to pick, and you need to do lots of trial and error and then hope you have good features and put them into some subsequent algorithm. And that's what we're going to do today. Today, we're going to look into object recognition. First of all, we look at some challenges. We do template matching, we do histograms, and we also will think about machine learning, because now we know how to calculate features and we can put them in a machine learning algorithm. That's the first part of today. And then we will look in the second part into convolutional neural networks, in which we don't describe features on our own that we put in a machine learning system. Rather, with a convolutional neural network, we learn features as well as we learn the actual vision task. And the neural networks are very helpful for this, so we don't need to think about features on our own anymore. But the neural networks come with certain pros, but also with certain cons, and we will contrast them to the other approaches. That's our agenda for today, and I want to know from you, first of all, if you have any questions about the lecture 2 weeks ago. If you're all okay, maybe send me a thumbs up or thumbs down if there are any issues and if you would like to ask some questions. All right. I also sent you an update in iLearn about your computer vision projects and for the deadlines. So then tomorrow, in 2 weeks or something, you can start submitting your proposals, which is just the topic and the names and the student IDs of the students in each group. Very importantly, make one submission per group. And then a few weeks later, we will have the proposal presentations, which are very, very short, just 1 or 2 minutes per group. But you will just briefly present your proposal, what you want to do. And I may give some hints or some advice, or I may see some challenges. And there could be other teams doing similar work. And that's why you all need to attend this proposal presentation. So this will help you to actually also see if someone else wants to do something similar and how to differentiate. But you've seen the roadmap in iLearn, so I don't need to repeat the dates and the deadlines here. So, object recognition. First of all, the term object recognition is not properly defined in the literature. And the term object recognition is overall a very general term that may refer to a whole collection of computer vision tasks that are related yet different. And I will now try to do an attempt to define these terms properly, and I try to make them distinct from each other. Yet that's only an attempt. If you look in the literature, some books may follow this, and some books or some textbooks, they may define these terms differently or may use them as synonyms. Yet we should be looking a little bit into the terminology and see how we can actually differentiate. So the simplest task actually when it comes to object recognition is classifying the whole image. What you want to do is you want to predict the type or class of an object in the image. And in fact, you would take the whole image and you would classify it. So you wouldn't look at the individual pieces. You would just try to classify the whole image. And this image here could be classified as dog, or the label when we use it for training would be dog. And you could have others with, I don't know, a car, an airplane, whatever. This is the simplest task when it comes to object recognition, because you just take the whole image and you want to classify the whole image. And this is something that works very well also if you try building your own convolutional neural networks. This is typically a straightforward task nowadays, provided you have enough label training data and you build a somewhat sophisticated deep neural network. But it doesn't need to be that challenging, or it doesn't need to be that sophisticated. This is something that was an issue maybe 10 or 15 years ago, but nowadays classifying images using, in particular, convolutional neural networks is something straightforward that works very well. As I said, convolutional neural networks are one attempt. We'll look into convolutional neural networks in the next chapter. In this chapter, we first look at some simpler approaches for classification. And this is overall a not that difficult problem. And then we can make this problem increasingly more complex. The next one would be localization. And localization means locating the presence of objects in an image and indicating their location with a bounding box. So this one here would be localization. We found an object and we put a bounding box around it. We have not classified this yet, because if we take the object that we have located and we classify it, this is often something denoted as object detection, because we locate an object, find its bounding box, and then we try to classify what's in the bounding box. So these three terms, or four terms, recognition, classification, localization, and detection, They are all not synonyms, even though a lot of people use them as synonyms. And I may sometimes do that too by accident, but technically speaking, all of these are different tasks. And object recognition, from our perspective, is maybe more like an umbrella term to describe a set of different tasks. But if you look into different textbooks, you may get different definitions. Just be aware that all of this is somewhat more difficult or increasingly more complex, and the detection task, as we define it, is obviously way more complex than the classification task, because the classification task is on the whole image, while we do localization, and then we try to classify what's in the bounding box. That's detection. Now we'll come back to the more general term object recognition. And object recognition is overall challenging because there's a lot of variation within our objects. So if we have our objects and we put them in different images, sometimes maybe one of the simpler tasks is translation. Translation means the object is not always in the same spot in the image, maybe not always necessarily in the center, but could be more shifted to the left or right or up and down. So this is one challenge. And later we will see with various object recognition techniques how we can use them to address some of these variations. Translation is a simple one. Then rotation is a somewhat more complex one, because rotation means the object is rotated. So it's maybe not always just, say, a human or an object being like straight, but maybe rotated by some degrees. Already will make the task somewhat more challenging. Scale is another variation. Scale means the distance of the object from the camera, or the size of the object in the image. In some training images, you may have this object very large, in others maybe very small. So these are some variations we have already seen a few times in this course, but there can be more complex ones like occlusions. Maybe the image, or maybe the object is partially occluded by others in the image. Or illumination. Based on the illumination, the object will appear differently. We can also change a viewpoint. There are also internal parameters of our camera that can lead to distortion or variation. For example, with some cameras, and you take a photo of some objects that have straight lines, they may not come straight out of the camera anymore into the digital image. So maybe some internal camera parameters somehow change that. Deformation, so the objects could be deformed. You also have a lot of variation within the class, because all of this is, say, for the same object that can be translated, rotated, scaled, occluded, whatever. But if we say we now care about cars as an object, there are obviously lots of different cars, and it's all the same class, but all of these cars may look very different. Same for birds, for cats, for houses, for dogs, whatever. So all of these are challenges. And then feature extraction. I told you in practice, or in a lot of vision problems, we're often not too sure which feature detector we would actually need to use. So we need to try different feature detectors, then have features, then put them in some subsequent system, maybe some rule-based system or a machine learning-based system or a neural network. But yeah, we just don't really know which feature detector to pick. So we need to try lots of different feature detectors. So these are some challenges when it comes to object recognition. And we will see now different approaches. Maybe the simplest feature detectors are templates and histograms that we can use to recognize objects. There are also so-called statistical shape models. This is something that was popular maybe 15 to 20 years ago in the computer vision literature. These were essentially also some kind of templates for a shape, but they could be customized with statistical hyperparameters. This is something that was popular in the past and isn't that popular anymore. So we're not covering this in this course because nowadays we use far more machine learning, and maybe 15 to 20 years ago, these statistical shape models were more interesting. But now we tend to use far more machine learning. With templates, we can try to find a pattern or a pattern of an object in an image. And what we do concretely is this is just a mathematical definition that doesn't matter too much for now. We will look at an example. This would be an example of template matching. So we have a template, which is the red one here, the red template, and we would try to find an adequate, or we would try to find that object in the image. And what we could do is we could move this template pixel by pixel on the X and Y scale, or X and Y axis, through this image. And when there's a huge overlap between the template and the object in the image, we would be very happy. And this is exactly what we're trying to do here. We're trying to figure out where the template matches the image. So we would have F, which are the pixel values, and H is our template. And eventually we try to determine the best fit of the template to the image. And this is where our correlation is maximized. And we're trying to move this template throughout the whole image. So if we move this around, we would have a low intersection with this object here, a low intersection with the palm, maybe a somewhat intersection with this object, but with this object we get a very large intersection, and it looks like a perfect match. And then we would have found our object. Because all we do is we have the template and we move it around pixel per pixel on the X and Y axis, and we try to find where the template has a huge intersection with an object. Looks straightforward to implement. What do you think could be some advantages of that template matching? If you have any ideas for, if you have anything in mind where you think this could be some advantage, or if you see some downside of template matching, you can also tell us this. You can turn on your mic. You can send us this in the chat. Just like to see a comparison, what you think could be an advantage of template matching and what could be downsides of template matching. And meanwhile, I got a private message. One student asked about the project, if you can already start working on your project. Maybe not yet, because we're still going through with the content. Before you pick a topic for your project, maybe wait until we finish the content. And then we'll talk about this again, because we have this lecture today and at least two more lectures, because we're even not halfway through the content. So maybe right now it's not yet the right time to finalize a project topic. You can obviously think about it, but first of all, focus on the content of the lecture. And in a few weeks' time, we'll talk more about the projects. So one person says a positive aspect of the templates could be we could find specific objects like traffic sign shapes. One person says can only be implemented for predefined shapes. That's true. One person says with these templates, we find objects in which we are interested. One person says we are not able to adopt to new shapes, e.g., for example, different animals. And this is correct. And this is what also a different person says, who said that this only works in rare cases when the objects look exactly the same. But if they have a somewhat different shape, then this doesn't work anymore. Yeah, this is true. So we are only able to find objects that look exactly the way they should look like, but once there's some variation, this doesn't work well anymore. Then one student says it's less time intensive than more complex pattern recognition approaches, and that's true. This one here is actually fairly easy to compute, and you don't need a huge GPU, whatever. But it's true that we can compute this very quickly, but it's also true that this has downsides and may take very short amount of time, but it doesn't work in a lot of real world settings. It may work very well in a controlled environment where we know exactly what the objects should look like. We know their size, their shape, and then maybe the illumination is not an issue, because if there was also illumination that could make these objects look somewhat different because of shades, whatever, then such a template matching also wouldn't work very well. What do you think about scale? Is this invariant to scale or not? So scale means the size of the object changes. Do you think such an approach would work? Or for rotation, would it work for that? Yes or no? Maybe let us know in the chat. We already got an answer. So this is not invariant to scale or rotation. It's invariant to translation, obviously, because the exact location of the object can be found. But once we rotate it or change its size, then this doesn't work. And if the shapes look somewhat different, this is the kind of stuff that these statistical shape models would address, the ones that I mentioned just before that were popular some 15 to 20 years ago. But nowadays we can do this far better with machine learning. But I'm not totally against the template matching, because if we're in some controlled environment where we can maybe control the size of the objects, the rotation, illumination, and we just want to check if the object is there or not, say maybe in some quality inspection process, then this could be perfectly fine. And maybe it works very, very well, and it just runs much faster and you need much less hardware than if you use a more complex approach. Yet, I think in today's world, in a year 2025, there's a limited number of applications for such template matching. But it's a beginning. We're starting to look now into increasingly more complex ones. We could also work with histograms. And the idea, what we do here with histograms, is we would extract different features from the image. We would use some feature detectors for this use case. And then we would try to build a lookup table for each feature. Concretely, we would use a hash table, and each entry in the hash table would vote for the model in the histogram. And then we would use a threshold histogram to determine candidate models. What does that mean? Imagine we have this image here, some flag of some country. And we will now run various feature detectors on here, and they will find us features, maybe edges, corners, whatever, or something more complex. And we have different candidates of what could theoretically appear in the image. So we would have bears, some kind of koala bear, and dogs. And for those, we know which features they have. And we compute the features in this image here, and we see this bear looks different to the bear in our histogram, because the bear is rotated, it's somehow deformed as well. And we see this bear we can compute lots of features from it. There are not a lot of features of this bear that would actually match to the features of the koala bear. There are quite some that would match with this dog, but absolutely more with the bear. And this would be the voting. So we would actually compute features from here, and the features that appear or that we have stored in the hash table for each of the possible objects we could find. We do a voting, and since we have the most votes for a bear, we say, well, we have most likely found with our histogram approach a bear in here. So this already works somewhat better than our template matching, because with our template matching from before, we would have not found this bear, because the bear is rotated and deformed. And that would have not worked at all with our approach before. So with this histogram approach, we can already find more complex variations. But we need feature detectors before. And again, in a lot of real-world vision tasks, we just don't know which feature detectors we would use. And we would need to do lots of trial and error until something like this works. Yet it's maybe, yeah, probably it's somewhat computationally more expensive than using our template matching, but maybe not too computationally expensive yet. And our next approach is now that we don't want to work with templates or histograms anymore. Rather, we will use machine learning. And nowadays, computer vision is very much based on machine learning approaches. This was not the case 20 years ago. 20 years ago, researchers and practitioners largely worked with templates, with statistical shape models, histograms, or some custom-made algorithms. And nowadays, we use a lot of machine learning because we rather want to learn from examples instead of describing templates, matching histograms, matching shapes. But what we need to do in machine learning is we have lots of machine learning algorithms available, for example, for classification. We can use for classification lots of different algorithms like support vector machines, k-nearest neighbors, tree-based models, Bayesian models. The problem is they don't work too well on actual image data. Have you ever tried, for the ones who are listening, have you ever tried to put an image as the input for a support vector machine or some other model, like a tree, a k-nearest neighbor, a logistic regression? Who has ever tried this? Maybe a thumbs up if you have tried it, thumbs down if you have not tried this. So you would put in the raw data. The raw data would be just the pixel data. You can try out such stuff, but it doesn't work very well in practice. Because if you have, say, an image that is 100 times 100 pixels, or bigger or smaller, whatever, and you could put these 10,000 pixels as the input for your support vector machine, your KNN, logistic regression, tree-based model, Bayesian model, that overall that doesn't work very well because you may be shifting the objects in the image, they could be translated, and then your classifier wouldn't really find any structure in there because you have your 2D data and you just map it to 1D as one big vector that you put in. And then this one doesn't work very well. So what you do in practice, you don't put in your raw data, and this is something that applies not only to computer vision, it applies to lots of other machine learning problems. You don't put in your raw data, but rather, in some cases in machine learning, you can obviously put in the raw data, but for a lot of tasks, you would pre-compute features. Sometimes for some sensor data, this could be some averages, some grouping, whatever. But for computer vision, we have seen various feature detectors before, like the Harris corner detector, and lots of edge detectors. And there are many more, and you would run them first on the image, and then you have your features, and you would put these features into your machine learning algorithm. This tends to work much better, but it's still limited because we just don't know which feature detector to pick. And this was one of the challenges of machine learning in computer vision, and all of this has made lots of progress in the last 10 to 15 years, thanks to neural networks. Because with neural networks, yes, we can put in the raw data, we can also put in features, but neural networks, under some constraints, they're able to self-learn adequate features from the data that we would then be able to use for learning our actual tasks. So the neural networks allow us to do both, learn features, and then use these features for our actual learning task. And this works particularly well for deep neural networks. And we will look into them now. We will look in this class specifically in convolutional neural networks. And I know we have one challenge in our degree programs. So most of the students here in this course, uh, they are from one of the two undergrad AI programs, the German language and the English language one. And while you're taking the computer vision course, you're taking your machine learning course. And not all of you have been exposed super deep to machine learning yet. So you could wonder, should we move the computer vision course to a later term? This could be done. We could move it possibly 2 terms later, because next term you will have your mandatory internship, but then it would actually be quite late to learn computer vision because of all the foundation courses that you need to take, like maths and statistics. We're also not really able to move the machine learning class to an earlier term. So because I know that you're also just now in your 4th week of the machine learning course, you're not an expert in neural networks yet. So we will do in this chapter first an introduction to neural networks. We will see how they work, how they can be trained and optimized, what algorithms we need for this, which is just general neural networks. And then we will see why they don't work very well for vision data and what we need to do so they actually work for vision data. Concretely, we need convolutional neural networks. And then we see how this works and we look at some other tricks of how we can improve them and some more advanced training methods. And we will look at selected neural networks, convolutional networks that have become popular. I know we also have other students taking this course. We have some master students taking this course, or some students from other degree programs that are maybe somewhat later or earlier in their studies. So some of you have learned more machine learning before, and some of you have learned less. And maybe you can send me a green sticker if you feel overall you feel okay with machine learning, and maybe a red sticker if you don't feel that okay with machine learning yet, because I also know we have exchange students and lots of other people in this course, so it's a very diverse course. And maybe some more response. We have half approximately. Now actually more red ones than green ones. And that's why we first will look a little bit more into how neural networks work and maybe some fundamental terms, and then you should be okay with them, and then we can use them for convolutional neural networks. One more thing, in your degree program, or if you are from the undergrad AI programs, in 2 terms from now, in the 6th semester, there's also a deep learning course, which is taught by Professor Wahl currently. He will study neural networks and deep learning with you in greater detail, but he will not discuss the convolutional neural networks again, because we're covering them here in detail in the computer vision class. But some of the other things, maybe some other neural network architectures or some more details about training neural networks, he will discuss in greater detail in the deep learning class. But in this course, I'll show you all the essentials you need for your project, and probably it will be a good preparation for your deep learning class as well. Now we'll have a revision. In our first lecture a few weeks ago, we started with convolutions. And we called them convolutions, or sometimes we called them filters or masks, whatever. Or kernels. So there were lots of terms for actually the same thing. And this is just another visualization of how we computed that. So we have an input image, which is this one here, which has pixels A, B, C, D up to L. So it's 3 rows and 4 columns, and we have this 2 times 2 kernel or mask or filter or convolution, whatever you call it. And this one can be moved through the image. And if we start in the upper left corner, so we would put this kernel W, X, Y, Z on A, B, E, and F. What we actually compute with this kernel is we multiply this element-wise. So the A times W, the P times X, and so forth. We have these 4 products, and we would sum them together. And then we have a new output. And that output would again also be just one element, which is just the sum of these products. And as we move the kernel through the image, for example, to BZFG, we would just do the same. So it would be B times W plus C times X plus F times Y plus G times Z. And we move it once more over here, ZDGH, we would compute this. And then we would move the kernel one row down, and it would be the EFIJ, and we would apply the kernel there and get this, and so forth. So when we move this kernel around, so remember this is a matrix with 3 rows and 4 columns, or an image with 3 rows and 4 columns, and we would apply this kernel. We would get a new image which has 2 rows and 3 columns. So we get a smaller output because we only want to put this kernel on a 2 times 2 input. We don't want to put the kernel just say, for example, here where we have a single element. Sometimes we may need to do this, and we'll see later how this works. But for now, we just put it on a 2 times 2 input, and then we move it around, and eventually the output will be a little bit smaller because we can only apply this kernel to 2 times 2 inputs. So this was the concept of our kernels or masks or filters or convolutions. And this is something we will need later when we build our convolutional neural networks. But first of all, we will look into very simple neural networks. We'll see what they are useful for. And then step by step, we will build more complex neural networks for vision. Who of you has ever trained a neural network or feels okay with neural networks? Maybe green stickers or red stickers if you have not explored neural networks yet. Actually, a majority for students who have not explored it yet. I will show you now how neural networks work and some of the underlying maps. A neural network works this way. We have input units at the very left. We have in this figure, so this figure is from the Bishop Pattern Recognition and Machine Learning book. And this figure says we have d many input units. If you want to put in, say, 100 times 100 pixel image, we would have 10,000 pixels, and we would put in these 10,000 pixels here as one vector, not as a matrix. We will later see how a neural network can work on matrix inputs, but for now, we would have 10,000 inputs. If you have 50 columns if you have tabular data and you have 50 columns, you would have 50 inputs. And eventually you have k many outputs, and your outputs could be, for example, 10. If you have 10 classes and you have, say, 10 possible classes and you want to classify an image, so you would put in the image and then you would make a prediction. We will later see how to do this. And you will get some values in the output units. And what this is also called, it's a feed-forward neural network, because we feed in input and we feed it through to the output layer. So we have an input layer and we have an output layer. And somehow we need to propagate the data from the left to the right. And later we would make a prediction for each of the output units, and we would use the class for which the corresponding output unit has the largest value. That would be the classification. Now, what we have in between is a so-called hidden layer. And the hidden layer is a layer of hidden units. Here we say it's m many. This number can be varied too. Maybe you ask yourself now, what's a good number of the size of the hidden layer? This is something we'll discuss later. And it turns out that in the most simple structure, all units of the input layer are connected to all units of the hidden layer. So every input unit is connected to every unit in the hidden layer. So X1 is connected to Z1, Z2, up to Zm. And x2 would also be connected up to xd to all the units in a hidden layer. And then all units in the hidden layer are connected to all units in the output layer. So Z1 would be connected to Y1, Y2, and so forth, and Zm would again be connected to all the output units. And the neural network may not just have one hidden layer. The neural network may have multiple hidden layers. Probably now you're asking yourself, how many hidden layers should the neural network have? This is something we will also discuss later, but there can be more than one hidden layer. And what you also see here is this x0 and z0. These are just the y-intercepts that you add on top, but how we add something together and how we do these calculations is something we will see in a few minutes. Neural networks are a very interesting computational model. Neural networks are very loosely inspired by how the human brain works. It's very important that these, sometimes we also call them artificial neural networks, so ANNs. Here I just call them neural networks in short, NNs. Neural networks do not work like the human brain. This is very important. They maybe work very loosely inspired by how the human brain works at the very most, but they don't work like the human brain. That's important. And these neural networks, they first of all fall into supervised learning because what I'm doing here is a classification or a regression that I put in something. So I have the input and I want to get something out. So it's a supervised problem in this instance. But neural networks can also be used for unsupervised problems, and neural networks can also be used in combination with reinforcement learning. In this course, we will largely look at them from a supervised perspective, but later in the course, we'll see a few other perspectives of these neural networks. So these neural networks, they're very helpful because they allow us to learn very complex patterns, in particular, complex nonlinear hypotheses. So this is something that is super helpful if you have very complex classification problems. And these neural networks are mainly used for discriminative tasks. So discriminative tasks would mean classification or regression. But in recent years, they have also become very important for generative tasks. For example, ChatGPT is also based on a neural network with a more complex structure. If you look at image generators, they are also nowadays often based on neural networks. So this is something that has become more popular in recent years. I've already seen neural networks being used for generating 15 years ago, so it's nothing new, but they just have become more popular and more powerful, in particular when it comes to text or speech or images. But in this course, at least in this chapter, we will largely look at them for how we can use them for classifying images. We could also use them for regression if we wish. That's just a tiny difference in the neural network. And these neural network architectures, they're highly flexible. So what I've just said is that all the input units are connected to all the hidden units, and then all the hidden units are connected to all the units in the next hidden layer and so forth. And then the last hidden layer, all the units are connected to all the output units. That's something we would call a fully connected neural network. This is the simplest structure, but you can build far more complex structures. You can also use neural networks for working with time series and for lots of other stuff that you would be exploring, for example, in a deep learning class. So it's a highly flexible architecture, and this makes them so interesting. The neural networks, very importantly, they not just have pros, they also have cons, and they actually come with quite some challenges. That's something we'll see later in this chapter as well. So I've been working on neural networks for maybe almost 15 years now, or yeah, 13 years now. Neural networks are something interesting and I like them, but I'm not a neural network fanboy because they also have some challenges and they're not a silver bullet for every possible learning problem. That's something very important to highlight. And that's why in a machine learning class, you learn other things as well, not just deep learning. And that's why we also see in this computer vision course, not just convolutional neural networks or transformers, but also traditional methods, because they all have their importance for specific tasks. Now, neural networks are nothing new. Actually, they date back to the 1950s in a simpler structure, in something that was called a perceptron. Who of you has ever dealt with a perceptron? Maybe green sticker or red sticker, if you have ever seen this. So the small majority for the perceptrons. So the perceptrons are a very simple type of neural network. It's in fact just one unit, which is this unit here, and you feed in your inputs. And for each input, you have a corresponding weight. And that's also what I want to say here. The weights of the neural network are these connections from one unit to another. And our goal later is to set these weights, these parameters of the model, in a way so that we can actually do our predictive task very well. And a very simple neural network could be just one unit, one output unit, and I have the inputs here and the corresponding weights. And in the most simple form, that's a so-called perceptron. And these perceptrons, they were initially believed to be extremely powerful, sometime in the 1950s or so. There was even some belief that a perceptron would make a computer walk and talk and see, but it turns out the perceptron is just a linear classifier. So it's overall a very, very simple model, and it can only do a linear classification. So if I have a more complex data set that cannot be separated linearly, the perceptron will not classify it 100% correctly. And this was understood then in the 50s or 60s that these perceptrons are actually extremely limited. And then there was a book called Perceptrons, and that book covered perceptrons, but the book was either very negative or was perceived very negative in that time. And then interest in neural networks was lost early on in the 50s, early 60s or 70s, because it was believed that these perceptrons were not powerful. But it turned out this is something was then understood probably in the 70s. If you have not just one perceptron, but many of them, and you combine them, that you have layers of perceptrons and multiple layers of perceptrons, and you interconnect them, then this actually tends to become very powerful and can learn very complex hypotheses. So you could just imagine each of these units here in the hidden layer as a perceptron, and then all the units in the output layer as perceptrons as well. And that's why these neural networks, they are sometimes called MLPs, multi-layer perceptrons. So you would have multiple layers of perceptrons. So you may, if you come across the term MLP, it's a multi-layer perceptron, and that's what these neural networks were also called in the past. This is an architecture that can become very powerful, but nowadays we don't typically call them multi-layer perceptrons anymore, because these units, they are not perceptrons anymore, rather they are logistic regression units. So logistic regression is just something that is a little bit more complex than a perceptron, because with a perceptron, the learning phase is quite unreliable, and it's overall a very unreliable experience to train a perceptron. But training a logistic regression model, which also does classification, is something more straightforward, because we have an error function that we try to optimize much better than in the perceptron. So these units are not perceptrons anymore, but they are actually logistic regression units. That's why I don't speak typically about multi-layer perceptrons, but about neural networks. And it was understood in the 1980s. So after that first drop of popularity in the 60s and 70s, they became more popular in the 80s. And this first period when they became unpopular, this is often also called the first AI winter, the first period when AI became unpopular because there were too many promises made and too little delivery, and the neural networks were only part of that AI winter. This also affected lots of other parts of AI. But in the 80s, all of this became more popular, and things like autonomous driving, handwriting recognition, all of this was already built to some extent in the 1980s, and a lot of these systems were based on neural networks. And convolutional neural networks also come from the 1980s, largely 1990s. And this worked well, but then again, there was another drop of popularity, say sometimes in the 90s, late 90s. What happened? Again, too many promises, and neural networks, they are helpful for specific problems, but they also come with challenges. Like neural networks tend to overfit a lot if you make them too large and if you don't have enough training data. Because when we look at the architecture of a neural network, and you imagine you just have one hidden layer with 1,000 units, and you have another hidden layer with 1,000 units, you would have 1,000,000 connections because each unit is connected to each unit in the following layer. So neural networks easily have millions or even billions of parameters, and very large neural networks today, they have hundreds of billions of parameters because you just have units and you interconnect them, and the number of parameters skyrockets. And a machine learning model with too many parameters tends to overfit. Overfitting means you learn the pattern in the training data very, very well, but you're unable to generalize to new or unseen data. And then in the 90s, there was this drop of popularity because these issues couldn't be fixed. And if you need a lot of training data, you also need a lot of training resources, and all of this was not available in that time. And then there were not a lot of people studying neural networks anymore, and it was even difficult to publish neural network work in, for example, machine learning conferences. So there was a lot of opposition to neural networks, but some people kept working on them, and then around 2006, 2007, something happened. New training methods were found to train neural networks better, so they overfit less. And also more data was available because the World Wide Web had spread more and computing time had become cheaper. And this is something that led to a situation in which neural networks got more traction as of 2006, 2007. And now for the last 15, 16 years, they have also been adopted a lot by industry. And this figure was from 11 years ago, and there was this question, but I just like the figure because it's very good. And that time the question was where all of this would go. What we have seen, it has really, skyrocketed, and neural networks have really gone through the roof. Uh, we see this with things like ChatGPT, DALL-E, and lots of other generative AI models, and not just Gen AI, but lots of other machine learning applications. And a lot of them are now based on neural networks. So we have not really reached that plateau of productivity, but rather it has totally gone through the roof. Yet neural networks are not a silver bullet, and some people notice this when they start using neural networks for tasks for which they shouldn't be used. But it's something we'll see later today. So this is the history of neural networks. And now, how do these computations work? For this, I have a slide, but we will develop this now step by step on the whiteboard, and we will look together at how neural networks work. Screen share should be working soon. When we have our neural network, and in the slides, you will see this with maybe a slightly more advanced notation, but we are starting this now just with the simplest possible notation. And we see we have our neural networks. We have our input units. We have a hidden layer, and we have an output layer. That's the input layer, the hidden layer, and the output layer. Then we've said that each unit is connected to each unit in the subsequent layer. And obviously, I'm not drawing all the connections now, but just some of them. And these are the weights of our model. So I'm just putting in some of them, obviously, not all of them, because I won't be able to finish. And these are the parameters. And these parameters, they're sometimes called W for a weight, or sometimes we use a theta for a parameter. For this, the literature is not very consistent. Either it's a weight or a W for a weight or a theta for the parameter in a model. And now I have these input values, and I want to calculate what are the output values. And for this, I need to do a forward propagation. And for example, to compute the value of this unit, what I need to do is I need to take one of the input values and multiply it with the corresponding weight. Then I take the next input unit and I multiply it with the corresponding weight. I take for each unit in the input layer, the input value, multiply it with the corresponding weight. So I have a lot of products, always value times the corresponding weight, and I sum together all of these products. So I have a sum of products. In, in the slides, I use a notation for something like this, that I say I have a weight ik, and in the lower index, in the upper index, j. What does that mean? The j is the layer, and the ik maps or is the corresponding weight from the one layer or from the one unit to the other unit in the next layer. And I have the corresponding inputs. So I have my xk, because I have, so this is the, say, input. And this here is the whole weight. So I multiply the weight with its corresponding inputs or corresponding inputs. So I have this product that I just described, and I need to sum all of these products together. For example, from index k is 0 up to sj, where sj means how many units I actually have in the previous layer. And I have these corresponding weights, multiply each of them with the input and sum that together. And this sum of product will be called, for example, z. So the set would be this value I have just calculated here. And the notation I use is set I of the next layer, j plus 1. But this is just one notation. If you look into other literature, you will see different notations. So this is just one of a lot of notations. And I'm doing this process not just for that unit, but also for the next unit, for the next one, up to the last unit. So I'm doing that process. Always calculate the sum of products because I have different weights. So I have one weight which goes from the first input unit to the first hidden unit, and I have a different weight going from the first input to the second hidden unit. And this is just one attempt how I can define this. So I say Zi of the next layer is the sum of products. But again, if you look into other books, they will use slightly different notation. But somehow you need to bring in the index for the layer you're looking at. For this, I'm using this J or J plus 1 for the next layer. And then the IK. So you need two indexes here because you need to have the corresponding weight from the one unit to the other unit in the next layer. So what we are just calculating is a sum of products. But this sum of products is oftentimes not the value we want to work with. Rather, we will transform it into a different value. And that's why we are now calculating I of j plus 1. And for this, we're just taking the z from before, or zi j plus 1. So the one we had just calculated here. And we are putting this into a function g, and this is called the activation function. Why do we need these activation functions? This sum of products could become a very, very large positive or a very, very large negative value, because we can also put in negative values. Weights may have negative values, and we could get very, very large positive or very large negative values, and handling them in the neural network could lead to lots of issues. So rather, we want to control this by using this activation function. And over the years, lots of activation functions have been proposed. And for example, one of the initial ones that has been proposed, does anyone know some names of activation functions? Maybe let's put it this way. If you know activation functions, send their names to the chat. One person has proposed the sigmoid function. This is the one we will look at now. And someone has proposed ReLU. We'll also look into ReLU. So we need the sigmoid function. And the sigmoid function is often written sigma of x. And this is 1 divided by 1 plus e to the power of minus x. And we can try to plot this sigmoid function and see what it does. X and y. And this is 0. And here we have 1. Actually, just put 0 here, then it's consistent. And do you know what the sigmoid function looks like if I try to plot it? You can also turn on your mic if you want to tell us how the sigmoid function can be plotted, or send it in the chat. Let's see. You can test this out on your own. You can say if you put in a very, very large positive value for x, then this will converge towards 1. So it will not reach 1, but will converge to 1. Because then it's 1 plus something very, very small. If x gets very large, then e to the power of minus x becomes very, very small. and then 1 divided by 1 plus something very small converges to 1. And if you put in a very, very large negative value for x, then this converges to 0. And when you put in 0 for x, then in fact, this is just 0.5. So the sigmoid function converges to 0 for very large values and converges to 1 for very large positive values. For x equals 0, if you want to see better plotting of this, look in the slides where this is plotted maybe in a nicer looking way. This is the sigmoid function. And the sigmoid function can be one possible activation function. And this activation function helps us to control the value that we wanted to compute up here. So this is the value we've just computed. And this one will be between 0 and 1. We're doing exactly the same for all the other hidden units. And then we have calculated the value of the hidden layer. And then we are doing exactly the same for the output layer. So for the output layer, we would also calculate the sum of products. So the sum of products for this unit would be the hidden value. So here times the weight plus the next hidden value times the corresponding weight and so forth. So we're just repeating that process. We're doing a sum of products for the output unit. And if the output unit is used for a classification task, we will again put this into the sigmoid function. So the output value of this unit will be between 0 and 1. We're doing exactly the same for all the output units. And eventually, we have finished our forward propagation. So we have put in some input and we have got some output. We need obviously concrete values for these weights. How we can determine them is something we'll see at the training phase. But for now, we just assume they have some value. And then we get these output values in the output layer. And if it's a classification task, we just pick the unit, for example, this unit that has the largest value. And the one that has the largest value would say, this is the class we wanted for our input. If we don't do classification, but if we do regression, then we don't do the sigmoid activation function for the last units. So we use for all the hidden layers, we use the sigmoid function, but we don't use it for the output layer, because for the output layer in a regression, we want to get a continuous value. So we don't put this in the activation function. Then we just leave the value as it is. But if we're interested in classification, and that's what we are doing today, we are using the activation function also for the output layer. Now, this sigmoid function is something that was popular for many decades, and it wasn't really questioned if this sigmoid function was so useful or not. And now some students mentioned the ReLU function that we can look at. So this was the sigmoid. And then there is the ReLU function. What does ReLU stand for? Who of you knows what ReLU stands for? I'll see who is responding in the chat. We're getting this. It's correct. It's the rectified linear unit. And what does it look like? The ReLU is 0 for all negative inputs and input 0. And for all the positive ones, it's just a linear function. This is the ReLU function. This one is another activation function, and there are lots of other activation functions that have been proposed over the decades. And you can look up the internet. There's a huge collection of activation functions, for example, TON-H and others. It turns out the sigmoid one was used for decades. And the sigmoid function is one of the reasons why a lot of neural networks tended to overfit. With just changing from sigmoid to ReLU, one of the consequences was neural networks started to overfit much less, something people had not noticed for a few decades. The ReLU function was proposed some 15 to 20 years ago. And just changing the activation function reduced the overfitting. And by the way, the training of neural networks became much faster because calculating the ReLU value is much simpler than calculating the sigmoid. Because for sigmoid, you need the exponential function and you need to call the sigmoid function many, many times in a huge neural network just for the forward propagation. But when you do the training, you also need to do a back propagation. You also need to call this very often. So it turns out this ReLU function has led to a huge improvement in the last 15 to 20 years. Neural networks overfit less. They still overfit, but less. And the training goes quicker just by changing the sigmoid function, changing sigmoid function to ReLU. So sometimes there are surprisingly simple solutions to a complex problem. We had assumed that our weight values are fine, that they are already set, and all we're doing is a classification. So we're doing this forward propagation in this feed-forward neural network. But in order to do the training, we also need to know how we can actually find the parameters. So how do we set these weight values so that the neural network works well? So we need a loss function, sometimes also called error function. And this is the one we need to optimize, or that's the one we need to reduce in order to find our parameter values. And one loss function that is popular is, for example, the squared error terms. So I don't give it a name yet, so we start with it step by step. We say we have our hypothesis, and we put in an example. So we have our training set, and we have concrete examples. So we have example I, and we put it into the hypothesis. The hypothesis is the neural network. So we say, I have my example, xi, predict its class. For this training set, I have m many examples. And for each example, I also have its correct value, its ground truth, which I call yi. And the predicted value can be may be different to our ground truth. So we will also call this here the ground truth. So what we can do is we could take the absolute error, but something that is very common is the squared error. So we take that error and square it. That means positive or negative error doesn't matter. We square it. And small errors impact little, large errors impact a lot. And we are doing this not just for one example, but for all m many training examples. So we say index I is 1 up to m because we have m many training examples. And this whole thing is then called the squared error function, something you see often in machine learning, not just for neural networks. And something you would sometimes do is, because this value may become very, very large, you actually want to normalize it and divide the sum by m, which is m many training examples, because otherwise the more examples you have, the far larger this error gets, and it may not become very practical to work with. So sometimes we just divide it by m. There are other error functions. So the squared error one you can use for both regression as well as classification. For classification in particular, there is a different function that we like to use. It's called the cross entropy. The cross entropy is a different error function that typically works better for classification problems. You can, for now, also just continue with your squared error, nothing wrong with it. But for classification functions, you would use the cross entropy typically. We'll later briefly look into the slides what the cross entropy looks like. Now, I have my error function. If you look in the slides, this is slightly extended. And unfortunately, the literature is not very consistent whether to use W for the weight or theta. So in the slides, what you would see there is a theta and a function j of theta, where theta is all the parameters. That's why in bold would look something like this. Before we have used W for weights. Now I use a theta here. Unfortunately, I'm also not fully consistent. And before we've also used these weights and we've used indexes for here. I just say I use my parameters or my weights in the neural network. So this is a slightly bit more abstract without using all these individual indexes. But whether we put W or theta just means the same here. Now my goal is I'm starting in the neural network with some initial weights. And initially, the neural network will probably not work very well on my training data, and I will have lots of errors. What do I do in order to reduce the errors in a machine learning model? Some of you said before you already feel very comfortable in machine learning. Maybe tell us, you can also turn on your mic. How do I now optimize this loss function? I want to reduce the loss, or sometimes called also error, in order to have better predictions. And for this, somehow I need to change the parameters. What can I do? No answers yet. Someone knows how we can reduce that error? Maybe thumbs up if you've ever seen something like this, or thumbs down, red if you have no idea how we can reduce this. That's fine. So we'll discuss it now. I didn't see. So one person proposes gradient descent. Perfect. So we will now look into parameter optimization. And what we are doing here not only works for neural networks, it works for a lot of other machine learning models, because here also this squared error has nothing to do with the actual neural network. The neural network was this H, but could also be just some other model like a logistic regression unit or some other model. And I want to optimize the parameters so that the error goes down. So what I have here is my error, J for cost. Sometimes there's a C for cost, an E for error, depends on the literature. And I have a weight or a parameter that I want to optimize. We just call this now theta. It's just a single parameter. And in the simplest way, what we could have is an error function like this. There are more complex ones. We'll see the more complex ones. So I'm starting with some initial weight value. And we'll make this slightly this. So let's say I'm starting with theta star, the initial weight, which could be zero or a random value, whatever. And I have an error up here. For now, we only have one parameter. We've seen before a neural network easily has millions of parameters. If I have 1,000 hidden layers, 1,000 hidden units, and another 1,000 hidden units in the next layer, I already have 1 million parameters. For now, we assume our model only has one parameter. What you learn in high school and what you revisit in your introduction to mathematics is how you can find the minimum of a function. And you just check, where does this function have a change of zero, and either I have a positive or either I have a maximum or a minimum at that point. This is something we could try here, but I told you we not only have one parameter, we possibly have millions or billions parameters. And then you're not able to find an analytical or exact solution anymore, but rather you need a numeric approach. And the numeric approach is called gradient descent. We will later look at why it's called gradient descent. And what I see is when I'm up here and I make my parameter value bigger, then the error would grow. And if I make the parameter value smaller, then the error would shrink. And the change in here is positive because the function is growing at that point. So what I need to do is I need to go against or in the opposite direction, opposite to the change at some step. And then I'm here. So I've improved my error. I've reduced the error and I have a new value for theta. And then I keep doing this again with some step size. I keep doing this until I converge. And when I'm converged, that means my error is only changing very, very little under some threshold. I'm stopping. And then I have found my value here for theta, which is the optimal value. This algorithm is called gradient descent. And we will look at now why it's called gradient descent. And we will try to write out what the algorithm just did. We would write just as pseudocode until convergence. We would update our theta. So theta is the old theta value minus the change of the error. So we said the error function is j. We'll just keep it for now as j. Well, we can say j of theta, just to highlight this. So j of theta. And we want its change. So what we can write then is, this is just the chain, sorry, not x, obviously. So we see how the error changes along the parameter value. So this is just the derivative. And that's what we've done before, because this minus here is important, because we subtracted the change. So we went in the opposite direction of the change until we converge down here. This is the simplest form of gradient descent. Now, it's not that easy in practice because imagine these steps here are very, very small. So we've done some big steps first and then smaller steps. Maybe these steps are super small and it takes very, very long until I reach the minimum. So this could be very slow. I want to influence the size of these steps. And what I'm putting here is an alpha. So I'm multiplying alpha with that change. And this alpha is called the learning rate. So I can make the learning rate maybe very big, then it converges very quickly. But maybe the learning rate is too big because the learning rate is a so-called hyperparameter. It's a global parameter in our learning problem that I need to set. If the learning rate is very small, then these steps are too small. If the learning rate is very big, what can happen is that I overshoot the goal and I could get something like this. So this could happen for alpha too large. That's what I don't want. So experimentally, I need to determine the learning rate for my problem, and it's a hyperparameter. Hyperparameter means it's a parameter, but not a parameter of the model, but the parameter of the training. So it's like a global parameter, or we call it hyperparameter. And I need to set this. In many real-world settings, the learning rate is something like between 0.001 to 0.1, something maybe like this, or maybe we add another round of zero. Somewhere in this range is often the learning rate, or maybe a 3 here, something like this. But this is something that needs to be determined experimentally, and we'll later see how we can do this. But for now, just trust me that somehow we can set the learning rate. And we can say, for example, 0.03 could be now our learning rate. And then gradient descent works this way. There's only one problem. So far, we have done this for one parameter, and we need actually a lot of parameters. So we can say we've done this now for one parameter. We can do this now for many parameters. And then it will also become obvious why this is actually called gradient descent and not just like derivative descent. Many parameters. We will write just as before until convergence. We say our parameter 1 is parameter 1 minus the learning rate times the derivative of the error function along our parameter. So we had here our j theta, and now theta is in bold because theta is a vector, because we have multiple parameters like theta 1, theta 2, and so forth. And I want to see how that error function changes along parameter 1. So I cannot work with derivatives anymore. Rather, I need partial derivatives. So I need to see how that function of multiple parameters keeps changing along our specific parameter. And I keep doing this not just for parameter 1, but say I have n many parameters. So theta n minus learning rate times j of theta, and this is not a partial derivative along theta n, and I have n many in here. So now we're almost done, but why is it called gradient descent? Who of you remembers from your math class what the gradient of a function is? If you remember what the gradient is, maybe send a green reaction. or tell us in your mic what the gradient is, or send it to the chat. I'll give you a moment. Waiting for you. So I saw some green reactions, or maybe either turn on your mic or send us in the chat what the gradient of a function is. So the gradient, well, one person says the rate of change, one says the slope of a function. Well, the slope of a function, this was the derivative. The gradient is something like this. The nabla of, well, we use J of theta is, it's a vector of partial derivatives. So we have the first partial derivative of J of theta along theta 1 up to, we have our J of theta, the partial derivative along theta n. So it's a vector of partial derivatives. Does that ring a bell for the gradient? Maybe thumbs up or green sticker or negative reaction. Maybe some more reactions. So this is the gradient. It's a vector of partial derivatives. And for this, we use this nabla sign here before. And what you see is actually we have the gradient up here because we have all these partial derivatives from 1 to n. So this whole, all these statements here can be rewritten by using a vector notation. So we can say now in vector notation, say again, until convergence, we can say that we have our theta, but theta now is the vector of all the parameters. And we update this as before. We said theta 1 is theta 1 minus learning rate times some partial derivative. So we say it's the theta, it's the vector, that's why in bold, minus alpha times, I'll move it slightly over here. So this was the learning rate before. Well, let's just write it nice. Learning rate. And then nabla J of theta. And this was the gradient from before. So all we have done was the multi-parameter gradient descent, all as before, but we just write it in a vector notation because here we have our parameters theta 1 up to theta n here again, and we subtract a vector multiplied each element by the learning rate. Are you all okay with this notation, with this vector notation? Thumbs up or thumbs down? Good. Only positive reactions. So now you know why this is called gradient descent and not derivative descent. Remember, we started with this optimization for one parameter, extended it to many parameters because the neural network has a lot of parameters. And then we've written it in vector notation. All of this applies not just to a neural network, but you can use it in a linear regression, in a logistic regression. The only question is what these partial derivatives look like. They look different depending on your model, like may look different in a linear regression than in a logistic regression. And here come the sad news. In a neural networks, in a neural network, calculating these partial derivatives is very tricky. There are various ways how we can calculate these partial derivatives in a neural network. There are some numeric ways how to calculate them, but that is very slow and very inefficient and not very precise. And there is a better algorithm to do this for us. And for this, we'll quickly come back to our slides, which I will share now. Just all I had shown you is also in the slides. We've seen the forward propagation. We've seen the activation function, the sigmoid function. We've seen the loss function, the squared error. And I've mentioned there are more sophisticated cost functions like the cross entropy. That one is mentioned here in case you want to study it on your own. And how to optimize the weights. We've seen this with gradient descent we've seen it for one parameter. We've called it theta, not W, but doesn't make a difference. And on the right, on the iPad, I've extended this and I've shown you how we come from one parameter to multiple parameters and then to using the gradient. Now the challenge is and this is just the gradient descent, just in a slightly different notation. It says repeat until convergence. I just wrote convergence. And what we have done is we have used batch gradient descent. So we have calculated these partial derivatives or the error of the partial derivative of the error for all training examples, because we have m many training examples. There's one challenge here. In practice, calculating these partial derivatives, even if we know how to calculate them, will be extremely slow because we may have millions or even billions of training examples. So calculating this here doesn't work too well in practice for big data or a very big model, because I need a lot of steps in my gradient descent until it converges. And I may need even a long time just to calculate one partial derivative. So this batch gradient descent, batch means using all the training examples, doesn't work very well. Instead, we use a stochastic gradient descent. Stochastic gradient descent would also be discussed in detail in a machine learning class or in a deep learning class. What I'm doing in there is I just take one or a few examples to calculate that error. So what I have here is, as before, I have my repeat until convergence, but then in the simplest form of stochastic gradient descent, I would go through all my m examples and I would calculate that error for my one example. Sometimes maybe not just one example, maybe you would put in, say, 10 examples or 100 examples in here, and for those you would calculate the error. This will give us not the real error, but an approximation, because the real error would only work, we would only have for all the m examples if jointly, but if we calculate the error just for a few examples, we get an approximation. And we get a better approximation if we initially randomly shuffle the data set. So this will not necessarily give us the right error, but an approximation. And I can calculate this partial derivative very, very quickly for this small subset. And I update my parameters. And I keep doing this in this inner loop, so either for one example or for, say, a few examples at a time, and I still stop with the outer loop until when I have converged. But it turns out this stochastic gradient descent helps us to converge much quicker because I quickly calculate changes. They are maybe sometimes wrong, and I may go in the wrong direction, and I may not necessarily go to the actual minimum, but sometimes I may go in the wrong direction, but overall, I make changes much quicker and I will end in the minimum much quicker. So this is what we need the stochastic gradient descent for. And there's also one piece of advice. The error function does not look that simple in reality. In reality, we will not have one global minimum. So this would be a convex cost function. Convex means one minimum, but we deal with non-convex cost functions. Non-convex means I have lots of minima and I want to stop actually in the global minimum because there could be lots of bad local minima, which still have very, very large values. And I want to make it to the global minimum. The gradient descent we use, and there are lots of variations of gradient descent that you would be discussing in a deep learning class. They will typically not lead you to the global minimum, but they aim to bring you to an okay local minimum. So in real, this function here is far more complex for a neural network. If you use, for example, a logistic regression unit or a support vector machine, what you aim for is a convex cost function. So it's a convex optimization problem with one minimum. But in reality, with neural networks, you have highly non-convex cost functions. And this makes training neural networks quite difficult. Also, I have said we calculate these partial derivatives, but somewhere we need to get them from. And we haven't discussed yet how we can get these partial derivatives. There are lots of ways how we can calculate them, but for neural networks, this is quite tricky. And there's one algorithm that has become popular in the 80s and 90s. It's called backpropagation. And what backpropagation does is it calculates these partial derivatives very, very efficiently. The main idea of backpropagation is I start very importantly with random weight values. The weight values are around 0 plus or negative, small values around 0. And I do a forward propagation of my data. So I feed in the data and I have errors. And initially the errors may be quite large because the predictions are just wrong. And then I back propagate. So from the output layer back to the hidden layers, I back propagate these errors. And I want to find out how much each parameter contributes to the overall error. And this is what backpropagation does. And as a result, backpropagation gives me these partial derivatives. How backpropagation works exactly is something you will see in your deep learning class. It's nothing we are doing here because we just use libraries that do this work for you. It's something you would investigate in your deep learning class or in a neural networks class, how backpropagation works. The literature here is not very consistent because sometimes in the literature, backpropagation not only refers to calculating the partial derivatives, but also to the gradient descent. So sometimes in the literature, this whole process of optimizing the neural network is called backpropagation. But technically speaking, all that backpropagation does is calculating the partial derivatives for us. And we still put these partial derivatives in gradient descent, stochastic gradient descent, or lots of variations of these optimization algorithms. But the backpropagation is not the whole thing, but the one that gives us these partial derivatives. So this is the introduction to neural networks. So what you would do in a neural network course. And now we will start applying this to very big neural networks that we can also apply to vision problems. So step by step, we are advancing. What is deep learning? Deep learning means we have lots of hidden layers. This is a term that has become popular in the last 15 years or something. And it turns out when you have a neural network that not only has a few hidden layers, but a lot of hidden layers, these neural networks tend to learn very complex concepts. This is from a Google experiment some 15 to 20 years ago. And what they attempted was they wanted to build a neural network, or they wanted to build a vision system that recognizes whether a human or a cat is in an image. Why is that interesting? We could try to build a rule-based system or some template matching system, but all humans and cats look different. So we're unable to classify the image well. If we use traditional machine learning, we would need proper feature detectors and then put that into some machine learning model. Also, that doesn't work too well. And it was noticed already in the 80s and 90s, if you have a neural network with a lot of hidden layers, they try to learn these features on their own. But this is something that could not be pursued in the 80s and 90s well due to lack of understanding, lack of training data, lack of resources. But nowadays, this is possible. And this was started to be understood 15 to 20, rather 15 years ago. And what they put in were images of humans and cats, and they were labeled correctly. And they put this in a deep neural network with a lot of hidden layers. And that neural network started to recognize on its own increasingly more complex features because you can try to visualize what a unit recognizes. And it was noticed that some of the initial units, they learn to recognize edges, very simple features. Later layers, like groups of edges, like a face of a human or face of a cat, and later layers, whole objects, groups of groups. And then the last, the very end of the neural network was only for the classification, cat or human. Most of the neural network was used for self-learning features. So you could just put in the raw pixel images, something we said before, we cannot put in a machine learning algorithm. With a neural network, we can do it. And it self-learns features. And this works for images, it works for speech, it works for text, for sensor data, that we learn on our own increasingly more complex features that we then use for some task, like classification or regression, whatever. But the actual task is just the very end of the neural network. So most of it is the feature detectors. Now, we're in a computer vision course. One challenge is I actually have a vector of inputs. So I have 10,000 pixels maybe I put in, but I don't preserve that structure anymore. I don't preserve this 2D structure, which is an image. So this kind of neural network works okay, but it can work better when we want to work on images. But there are more challenges. And I've told you before that maybe these are the questions that came to your mind. How many layers do I need? How many hidden layers? How many units per layer? An initial rule could be the more hidden layers, the better. I just put in more hidden layers and I learn more complex features. And I put in very large hidden layers. But this will be computationally heavy and it may lead to overfitting because machine learning models will tend to overfit so that they learn the pattern in the data too well, but don't generalize if I have too many parameters. So if I have a lot of parameters, I would overfit. How can I combat the overfitting? Maybe I need more training data. Maybe I need to take some other tricks. How much training data do I need? How long will the whole training take? All of these are questions that need to be addressed. Also, which activation function should I use? So I told you this ReLU, only the red one here, only became popular 10 or 15 years ago. Before, sigmoid was used a lot. And sigmoid works okay, but now in retrospect, it actually led to super slow and overfitted training. And with ReLU, and nowadays there are lots of variations of ReLU again, this works much faster with less overfitting. There's also a very interesting website that I briefly want to show you. Just need a moment to open this. Then I'll switch to the screen share again. There is the screen share is coming now. There's the TensorFlow playground. Has any one of you ever seen this? Maybe thumbs up or thumbs down if you have seen this. So all the theory we've just discussed is something you can practice in the TensorFlow playground. TensorFlow is a library for neural networks, and there's a playground, so you can run it in the browser. You have a data set, you have two classes here. So you have the one circle and an outer circle, and you just want to classify, you want to learn a function to separate these two classes. With the initial settings, this works. And what you can do is you can choose what you input. This is just simplified. It puts in features, very simple features, not the XY coordinates, but very simple features that try to separate certain things. And you have neurons in each layer. So I have in the first hidden layer 3 neurons, then I have 2. I can put in another hidden layer and I can reduce the number of units. I can increase it. I can use an activation function. I can use tanh, sigmoid, linear, ReLU. I can play with the learning rate. Regularization is something else to this L1 and L2 regularization is something you would also learn in a machine learning course that helps us to address overfitting, and you need a regularization rate. And you can also add noise to your data set. So noise means you have these classes overlapping, and there are more complex data sets. Like this one is simple, this one is simple, this one is more tricky. And we see my neural network initially doesn't work very well because I still have a very large loss on my test set, which is the test loss or test error. But I also want to reduce, and initially I want to reduce the training loss. Training loss would mean the loss on my training data, which I want to be very low, but it still needs to generalize. And generalizing means I also reduce the test loss a lot, because overfitting would mean I have a very low or even zero training loss, but a high test loss. Test loss would be on additional test data that was not used during training. And you can try to build your own neural network here in order to separate these two classes. This is just my initial approach. You see, it doesn't work very well yet. You can build a better neural network trying to separate these classes by just taking everything in account we have learned. For example, changing the learning rate, but if you make it too small, it's too slow. If you make it too big, it overshoots and it will also not generalize. You can work with features, and once you have found a neural network that separates well, you can try to add more noise and make it more complex. This would be one of your homeworks, playing with this TensorFlow playground and see if you've understood the concepts about neural networks. But today, we want to advance this, and we actually want to look into vision problems. And we will now build a concept of convolutional neural networks. And convolutional neural networks are neural networks specifically tailored to vision problems. And ideally, they help us to become invariant to translations, because with our standard neural network or even a deep neural network, we are not invariant to translations because we have an object in the image and we move it around in the image, and the neural network may not be able to recognize it well because we have our 2D input and we have turned this into a 1D vector input. So our standard neural network, even if it's deep, does not have an understanding of the 2D image because we put it in as a 1D vector. So we include all the rows we include all the rows together and put it in there. And a convolutional neural network is an architecture that tries to address this. What the convolutional neural network does is it helps us to become invariant to translations and some degree of rotations, in fact. A neural network works on the 2D image input. Now, not turned into 1D, but the actual image. And it has a convolutional layer. And the convolutional layer has various convolutions that we will soon see how to build. And these convolutions, they look at a smaller section of the image. And we have various convolutions in here in our convolutional layer. And this will be later the ones that learn features, that learn to recognize certain objects or certain elements in the image, no matter where the object is in the image. And after the convolutional layer, we have a subsampling layer, which further compresses the information from the convolutional layer. And we will have very high level features coming out of this subsampling layer, so the layer after the convolutional layer. And this is the idea of a convolutional neural network that we will build now. Convolutional neural networks are something that was already described in the 1980s, rather 1990s a lot. But nowadays, this is combined with deep learning, that you maybe have a lot of convolutional and a lot of subsampling layers. And if you combine such layers and you build a deep architecture of many pairs of convolutional and subsampling layers, you tend to build very powerful neural networks that can learn to recognize very complex features and use them for the actual task, for the actual downstream learning task. So welcome back from the break. And now that we have motivated convolutional neural networks, we will see how they work. And they're overall super helpful because they can work with 2D data and work on images. And it turns out over the years, they've also been adopted to other problems, not just vision data, even text data and so forth. So they can be adopted to this, but we'll look at the vision part today. We've seen convolutions before. When we started with today's chapter of convolutional neural networks, we saw we have this kernel and we can move it through an image to calculate outputs. And we multiply them element-wise and sum these products. Now, this is just one more example, but we've seen this more generic before. When we now look at these convolutional neural networks, they use convolutions, and actually they have a few very interesting properties. Concretely, we look at sparse interactions, which helps us that the neural networks can be trained efficiently and don't tend to overfit too much. We will also we will look at spatial arrangement, how we can move these masks or kernels around. We'll look at parameter sharing and equivariant representations. What are sparse interactions? Sparse interactions address the following issue. I've said in a traditional neural network before, every output interacts with every input because we have these fully connected networks. And convolutional neural networks, they reduce the overall number of parameters by using sparse interactions. And this helps us to make these kernels smaller because we have lots of these kernels or convolutions that look at different parts of the image. And that means we have to store fewer parameters, reduces the memory requirements, training time, but also leads to statistical efficiency. And the kernels are usually much smaller than the image. So these pieces here, they are much smaller than the actual image. Or the kernels here, this is a kernel that looks at a piece of the image. They are much smaller. They don't look at the whole image. And this is a notation that is also quite common in the literature. What this means is I have one kernel that has its receptive field that looks at this one here, but we have more kernels. So we not only have one kernel looking at here, but we have multiple kernels looking at there, just with different parameters. Different parameters means maybe this kernel here recognizes certain parts in that part of the image, while this kernel recognizes something different. So we have different kernels looking at the same receptive field, just trying to find different features, because these kernels, all they are eventually sophisticated feature detectors that are learning purely from the data rather than being predefined as what we have done with edge detection and corner detection. And these sparse interactions lead to a situation that is the following. So we have these X's and these S's. What does that mean? The S are the output units. So what comes out of the or the convolution. Um, and the X are the inputs. And in a traditional network that is fully connected, we have something like this. All inputs go into all of these, into the next layer. And now the next layer are these convolutions. And each convolution is only affected by some of the pixels. Like, for example, pixel X3 is only relevant to the convolutions S2, S3, and S4. This is now from 1D. Obviously, with the convolutions, we will address 2D, but will become increasingly more complex with this. So overall, we have less parameters with these sparse interactions than in a fully connected neural network. And there's a lot of text here. This is from the Goodfellow deep learning book. So there's just more text if you want to do your revision. And essentially, it's just an essence of what I'm saying. But feel free to do that revision or to look at these texts here, these captions when you do revision. And now we can actually wonder, how can the neural network eventually, at the end, look into the whole image? Because so far we have built convolutions that look at two parts of the image. And eventually we will stack these convolutions. We have one layer of convolutions, and then we have another layer of convolutions. And then initially, this, as initially, for example, this convolution could look at these three inputs. We have now a whole layer of convolutions, and we stack on top another layer of convolutions. So this convolution can look at these three convolutions, and they look at these pixels. So eventually, as we stack these layers of convolutions, the receptive field is growing. And the fact that we look at three, like this convolution here looks at these three pixels, the width is 3. This is something that is obviously not set by nature, but something we can customize. This would again be a hyperparameter of the convolutional neural networks. There's a lot of text here about the spatial arrangement. And again, the text here is for your revision. Or for further reading, if you wish, I will just show you the essence. Before I had said we have a kernel, and the kernel can be parameterized, can have a certain size, can be 2 times 2, can be 3 times 3, whatever. And we can not only shift it through the actual image, but what we can customize is that we can do like 0 paddings around it. Because before, when we earlier today looked at kernels, we saw when I applied a kernel to an image, the output will be smaller because the kernel will always just look at a 2 times 2 input, but we also have these ones. And then, in fact, the output image would get smaller. This is something I can also influence, and I can add these 0 padding, so zeros around, and how many zeros I put there, the width and height, again, can be customized. And with that, I will influence the size of the output. What I can also customize is before, and it's just a lot of text, just in essence, what I have said or a different reading for your revision. In addition to these 0 paddings, the question is how do I move this kernel around? Before we said we put the kernel here, then we shift it once by right, and then we do this for the lower columns. But I can also set a hyperparameter which is the stride in X and Y for height and width, or for width and height, just to be X and Y correctly. That means how I shift that kernel around. Do I shift it one by one? Does it make bigger jumps? And this is something I can customize as well. If I make bigger jumps, values bigger than 1, 1, the output will also shrink. Uh, there are also some equations for this, how this belongs together. Probably you're now wondering what should be your stride, how many zero paddings should you put there. This is something you can do trial and error when you do it for the first time. When you customize your neural network, you set the hyperparameters, you could try to experiment with this. If you have some domain knowledge about your data and the problem, maybe this could help to set a proper stride and zero padding, or you will use a pre-trained neural network where someone has done this for you already. I'll show you in a few slides these pre-trained neural networks that do exactly that for you, so you don't need to find out by trial and error how to set these hyperparameters for the convolutions. Now, there's one more thing, it's called parameter sharing. Parameter sharing means something we saw before was you have, say, you have this convolution here, and you have that convolution here. And in fact, what you could try to do is that you don't train always new convolutions for each part of the image, but you actually train the same convolutions that look at different parts of the image. We saw before when we had this receptive field, I told you we have multiple convolutions that look at the same receptive field, but we could use these convolutions to look not just at the same receptive field, but they look at different parts of the image with the receptive field. So what we are doing is we're training these convolutions to be feature detectors, but some features may not always appear in the same spot of the image, but in different parts of the image. And that's why it could be helpful to have the same small feature detector that we can apply all over the image in order to find the features we're trying to look for. And with parameter sharing, we're doing exactly that. So this is just essentially written here in the figure, in the caption, that we use the same feature detector throughout the image. And we have not just one feature detector, but many, but we not always train new feature detectors for different parts of the image, but rather we move around these feature detectors. And yes, in the chat, this also contributes a little bit to the detection of rotated features. Not fully, but a bit. It mainly addresses translation, that the same stuff is moved throughout or translated throughout the image, but it also helps us to address some rotation if we use the concept of parameter sharing and building these feature detectors and being able to move them throughout the image, and that they not always look at exactly the same locations. So this helps us to generalize and reduce the number of parameters in the model. And that's overall very helpful because it also tends to overfit less. There is another smaller concept called equivariance. It's something that is actually just a consequence of what I have explained, but feel free to read equivariance in your revision if you wish. What we have built now are the convolutions in the convolutional layer. And I've said to you, after the convolutional layer, we have the subsampling layer. This was in the initial figure that we looked at for a convolutional neural network. We said after this, we have the subsampling layer. And we probably just go back a few slides and we see it. So we've built now the convolutional layer, and next we are building the subsampling layer. And in the subsampling layer, we are again doing a compression. Our subsampling layer has something like also a receptive field that it is looking at the convolutional layer, but it's not building a convolution, rather it's doing a very strong compression. And that compression is often just a summary statistics. For example, we look at these values in a certain field, and in that field we have multiple convolutions, and they have a specific value when they look at the image. And from these values, I just want to calculate a summary statistic, maybe the maximum, the average, or some weighted average, or minimum. Oftentimes we use the maximum. And this is a huge compression of what these convolutional feature detectors just look at. And pooling helps us, again, to build even more high-level features from what these convolutions have seen. And this, again, contributes to an invariance in the input. Now, this is another figure that that actually just continues what we had discussed. What we had discussed was the input that we look at, and in our convolutional layer, we build lots of features, and we have these convolutions that look at different parts of the image, and we have a lot of these convolutions. We've just seen that. And we've said we do the subsampling, which are these summary statistics of different areas in these convolutional feature maps. We could say we're done here and we have very high level features, but maybe we want to continue this. And before we've seen with deep learning, if I have a lot of hidden layers, I can learn increasingly more complex features, like first these edges, then groups of edges, groups of groups. And if we continue this process, say now we build convolutions from these subsampling values, and then we subsample these convolutions from subsampling values again. If I continue such pairs step by step, then I actually get very high level features over time. And modern neural networks not just do this twice, but maybe many, many times. Sometimes there are variations. Certain neural networks, they leave out the subsampling. They do maybe a convolutional layer followed by a convolutional layer, followed by many more convolutional layers, and then maybe some subsampling layer later. But everything here in blue is just the feature detectors. All we are learning is features. And this time we are not describing features, but rather we are learning them from the data. And what is coming next is the actual fully connected neural network. The fully connected neural network is often maybe just one or two hidden layers, often two hidden layers, or say 2 or 3 layers of weights to be precise. And that's all you need for the actual learning of your task. You don't need hundreds of fully connected layers. Just 2 or 3 hidden layers is usually enough. And what you're feeding into these fully connected layers is not the raw data, but rather very high level features that you can either describe with a feature detector or you learn these features. And that's what our convolutional neural network has done. So most of the neural network is actually just the feature detector, and the smaller part is the actual learning of the task. Say the learning of the task is whether to classify or regress, whatever. And you have most of the neural network is the feature detector. So this is how convolutional neural networks work in the era of deep learning. This is far more sophisticated than was done in the 80s and 90s when there was just maybe one layer of convolutions and one subsampling layer, or just a few of these layers. Nowadays, we have a lot of these layers stacked, and then we do the actual learning of the task. And this is possible because we have more data, better training algorithms, and more computing power available. All of this was not available in the 90s, and that's why we nowadays have very good vision systems that work extremely well. Now, we'll look a little bit more into the theory. I told you one of these challenges is in our optimization algorithm, gradient descent. The question is, how do I get these partial derivatives? And we looked at backpropagation, but in fact, it's not that straightforward to use backpropagation because it's all subject to the actual architecture, so to the actual structure of the neural network. This is just a high-level mathematical description of my problem. My neural network is a function that maps input to output, and say I have an n-dimensional input and an m-dimensional output. So a map from an n-dimensional input to an m-dimensional output. Sometimes this is just a vector, but the neural network could also map the input maybe to a higher level structure, maybe generate a new image or something. So it's not always just a vector of outputs or a classification, but the neural network can maybe generate a new image, a text, whatever. And actually what I need are all these partial derivatives, and the partial derivatives are all subject to the neural networks and the parameters. But what does the neural network look exactly? Before, we've seen different architectures like this one and before simpler ones. And nowadays, every day, thousands of new architectures get proposed on the internet. This is something that was not possible in the 80s and 90s because the big challenge is, aside from computing power and data, how do I find the partial derivatives for any neural network and any loss function? We've looked at the loss functions before, like squared error or cross entropy, but there are lots of other ones as well. And how do I change the activation functions? All of this has impact on the partial derivatives. And the approach in the 80s and 90s was the following. When you have a new architecture of a neural network, you need to do this on your own on a piece of paper. You need to think about how the backpropagation runs and what these partial derivatives will look eventually. So you would need to come up with an analytical solution on your own, which is subject to the structure of your neural network, the architecture, the activation functions, the cost function, and so forth. And if you just make one tiny change to your neural network, you can start from scratch figuring out what the analytical solution of your partial derivatives would be. So it's a not automated process. So you would need to run backpropagation on a piece of paper in order to find this out for your structure. Very challenging, very time consuming, error prone, and needs to be done for any changes in the neural network. And when you look at publications of neural networks until the early 2000s, mid 2000s, or early 2000s, then until 2005 or something, most of the work when there were papers proposing new neural networks was actually doing this backpropagation and figuring out analytical solutions for the partial derivatives that could be plugged in the gradient descent. Once you have this, obviously it runs super efficient in a computer and you get very accurate results. But you actually all the time now we're making changes to neural networks, and doing these derivations may take weeks because it's quite tricky. When I studied machine learning in my master's, we actually learned how to do this on sample neural networks on our own, how to apply the backpropagation algorithm in order to figure out these partial derivatives. This is not fun at all. Well, it's fun from an academic perspective and learning how to do the backpropagation on your own to find these analytical solutions. But it really does not lead to much innovation because just tiny changes to your neural network will lead to lots of manual work. You could think about, well, let a computer do this. We actually want symbolic differentiation. So symbolic differentiation would mean we use some advanced computer algebra system like Mathematica, Maple, whatever. Not MATLAB, very importantly. MATLAB is not a computer algebra system, only has some extensions for symbolic differentiation, but like Maple or Mathematica, you can use them, but it's very inefficient and it doesn't really scale to sophisticated neural networks if you use symbolic differentiation to find these analytical solutions of your partial derivatives. And you need the partial derivatives, and ideally they should be quite accurate. So doing symbolic differentiation or the analytical solution is great, but symbolic differentiation is too slow and doesn't really scale to very large neural networks. We could think about, well, we can approximate every partial derivative because we have our neural network and we want to see how does the error change subject to a parameter value. And every derivative can be approximated. This is how derivatives are introduced in your first lecture or in high school. When you wonder how can we actually find derivatives, you say, well, I have a small value h that converges towards zero, or we move it close to zero, and we plug it into the function f of x, where x here is our parameter, plus value h minus f of x dividing by h. And it turns out when h is very, very small, you can approximately use this statement here, that you just use your very small h and plug it in and find a numerical approximation of your derivative. And this works in 1D, it works in higher dimensions as well. So you can do this, but this numerical differentiation, it's one advantage, it's very easy to do, but the problem is you get very inaccurate results because you just don't know which h you should really pick that is small enough. If you try to plug this into your gradient descent, it will become super slow because you need a lot of partial derivatives in each loop, and you have a huge neural network. So this will lead to not only a very inaccurate solution, but also to a very slow execution, and your results will probably be not numerically stable. So this is also not too great. You can use the numerical differentiation maybe for debugging. If you have, I don't know, find the analytical solution and you want to see if it's actually more or less, if it's actually correct, you can test it and you can compare it to the numerical differentiation. This will not give you a proof, but maybe an approximation whether your analytical solution is actually okay. But still, none of this is really convincing. And then what we are benefiting now from is in the last, say, 15 years is automatic differentiation. It has become very popular in neural networks for the last 15 years. And the automatic differentiation, first of all, it looks something like symbolic differentiation, but it's important, it's not symbolical differentiation. It's actually something quite different. And the automatic differentiation refers to a set of techniques that numerically evaluate the derivative of a function specified by a computer program. But this is not the numerical differentiation and not the symbolic differentiation. It actually does something quite different. How it works exactly is there are lots of resources on the web, or you would see this in a deep learning class, but the automatic differentiation is very helpful because it will give you very good partial derivatives, and it's still you don't need to take on any manual work when you use a library that has automatic differentiation implemented, and it will give you these partial derivatives very quickly. So this is very helpful when you start building your custom neural network architectures and you don't want to manually compute the partial derivatives and you don't want to calculate them numerically or symbolically, but the automatic differentiation is, I think, one of the masterpieces in optimization that is now available to neural networks for the last, and it probably largely been used for the last 15 years or something. And this helps everyone to easily build their own custom neural networks. The actual automatic differentiation is older than 15 years ago. We could look up when it was actually proposed, but it was largely applied to neural networks in the probably last 15 years or something. So feel free to read a little bit on your own about automatic differentiation and why it's so helpful to neural networks. And it's something that has just become very popular for neural networks nowadays. And like this, you can build your own custom architectures. The good thing is now when you want to build neural networks. You don't need to implement these algorithms from scratch. When I studied machine learning in depth in my master's, we started building our own neural networks from scratch, and I've tried this kind of stuff. It's a great learning experience, and Professor Wahl does some of this in his deep learning class. In practice, once you want to ship real code that works efficiently, you need to use neural network libraries. There are lots of them available. TensorFlow appeared almost 10 years ago, which was released by Google. And the idea of TensorFlow was Google had built its own deep learning library, implementing all these algorithms efficiently, as well as automatic differentiation. And all you need to do is in Python, you use Python to build a high-level neural network, and you would describe obviously how it works, how to train it, but all the low-level work would be done for you. Keras came up then. Nowadays, Keras and TensorFlow have been largely merged into one big thing. PyTorch is a different library that is popular. For the projects, you're free to choose any libraries you wish. When I worked with neural networks before TensorFlow appeared, I sometimes used something called Lasagne. Lasagne was popular about 10, 12 years ago. And the name means you have different layers and you stack them like in a lasagna. And that's why the library was called this way. But nowadays, Keras, PyTorch have become popular. There are some other ones as well. And they are really great because they implement these algorithms very efficiently for you. Plus, they come with numeric differentiation. You don't need to worry about all these low-level details. If you look at an example for Keras, how to build your own neural network, your own convolutional neural network, you would just import Keras, you would create your model, and then you would specify each layers. So a sequential layer would be a fully connected layer. You would, no, it would be a feed-forward neural network, and then you are adding the different layers to this feed-forward neural network, like a convolutional, like convolutions with 3.3 kernels and 32 of them. You would have the ReLU activation function. After this, you could put a max pooling, so pooling summary statistics with the max function, looking at 2 times 2 windows. Then you would have another convolutional layer, followed by another pooling layer, followed by another convolutional layer, and so forth. So you can build this in Keras super high level. When the first version of TensorFlow came out, you could not exactly do it this way yet. It was still more code, more low-level code in Keras, in TensorFlow. But now TensorFlow has obviously been improved in the last 10 years, and it's been largely merged with Keras, and now it's super high level. There's still some questions you need to wonder about. How many hidden layers do you use? How many convolutional layers do you use? How many pooling layers? And how do you organize them? How big do you make them? So what's the number of units per layer? We've seen before briefly the TensorFlow playground, and we've seen all these hyperparameters you need to optimize. The number of layers, the number of units per layers. All of this are hyperparameters. There are more, like the regularization factor, the learning rate. And how do you find these hyperparameters? And this is in fact not that easy. What you can do is trial and error, and over time learn how to build good neural networks on your own with the right hyperparameters. Because if you pick poor hyperparameters, the whole neural network will probably not be trained very well. There are some structured approaches that you could take. For example, you could take grid search. Grid search means you have these hyperparameters and you would define possible values for the hyperparameters. So we could say, I allow 1 hidden layer, 2 hidden layers, up to 10 hidden layers. and I allow 100, 200, 500, and so forth number of units per layer. And you have regularization factors, they would maybe be small values like 0.001, 0.03, and so forth. So you would come up with possible values of your hyperparameters, and with grid search, you would say, try out all of these combinations. What do you think will happen if you use grid search on a large neural network with a lot of hyperparameters and possible values? If you have any ideas, send this to the chat or turn on your mic. What could be happening if I use grid search like this for a very large neural network? You have any ideas, maybe signal this with some reaction and I'll wait for you. You can also turn on your mic. If you if you're overwhelmed and think, well, you don't know what the consequence could be, maybe send me some negative reaction. So I see that you don't see the problem. So with grid search, I will have this combinatorial explosion. So I need to train one neural network for each of these settings. So one neural network with one hidden layer, like 100 units, and some regularization factor. Then I change the regularization factor, and I have lots of possible values for each of these hyperparameters. And each training possibly takes long because it's a big neural network that I each time need to train. And then I would pick the neural network that has the lowest test error. But I have lots of hyperparameters and lots of possible values. So I really have this combinatorial explosion, which just take very long until it's finished. So not practical. And for example, I need to I need to define the number of layers, say 5, 6, say 5, 10, 20, I need to come up with these discrete values, as well as for the regularization factor. Is 0.01 or 0.03 useful, or is there maybe some regularization factor in between that is useful? Well, I don't know. And that's why I would use something like randomized grid search. First of all, a randomized grid search would not try all the possible combinations from the grid, but it would randomly draw from each variable some values, and it would maybe do 50 attempts or 100 attempts. I can control this. It will not give me the optimal solution, but very quickly it will possibly give me quite a good solution of the hyperparameters. And very good grid searches, randomized grid searches, do not work with discrete values, but rather, or maybe not only with discrete values, but sometimes I can just define ranges. I could say, well, my regularization factor is between 0 and 1, randomly draw from that range. I don't split that range into discrete values. I only define the range, and grid search will randomly draw from these intervals. This is something super helpful because I don't need to come up with discrete values, and maybe none of them may be very good. This is rather done by a randomized grid search. And such optimization techniques exist in neural network libraries, but they also exist for other machine learning libraries, like, for example, for scikit-learn. You also have in other models this issue of hyperparameter tuning, like in a logistic regression, in a tree-based approach. There are also hyperparameters, and you need to optimize them. And what you typically do is a randomized grid search. But still, all of this is a lot of work that we need to take. How about we let the computer automate that work for us? And this is what AutoML, or automated machine learning, stands for. AutoML describes a large process of automating some of that work. Ideally, say in the far future, the big wish would be that AutoML would be so advanced, you just give your data set to a machine learning algorithm and say, hey, train me a model and do the predictive task. But we're not there yet, and I don't think we'll be any time there because we still need to look into the data. We need to do an exploratory data analysis. We need to pre-process the data and cleanse it. And automating this is quite difficult because we need domain knowledge. So today's AutoML libraries are very limited when it comes to that. But what they can do actually well is they can help me to optimize these kind of things. Like how many layers do I need? How many units? How many regularization factors? And so forth. Or which value for the regularization factor, as well as the learning rate and others. So AutoML frameworks, they would try to find a neural network for me that does that. So it would automate my machine learning task. And this is overall really cool because AutoML libraries don't just naively. So there's some question here if anyone else lost the audio for a bit now. I don't know. Maybe there was some connectivity issue, but can you hear me well now? And maybe tell me for how long you didn't hear me.
Or like we did not hear you for like 20 seconds, but now we can hear you.
Okay, so then I'll just repeat quickly. So AutoML is something far smarter than just randomly trying a grid search. What it does instead is it will try some initial combination of the hyperparameters, but then it will not naively try something totally new, but rather it will use machine learning, usually some Bayesian optimization in machine learning, to find me very quickly a better set of hyperparameters. So good AutoML libraries use machine learning to optimize my hyperparameter search. This is overall really cool and possible now for probably 8 or 9 years in a very good and reliable way. Our hope would be that in the future, this obviously works better, that we could even do more steps like data preparation, feature engineering. This all exists to some extent today, but it's still quite limited. And probably some of the work is extremely difficult to automate because you also need domain knowledge when preparing the data. But AutoML is really cool. And all I've talked about, or actually most, what you're learning in your machine learning lectures. So most machine learning lectures are about building different classifiers, regression models, whatever. And you learn all these different models, support vector machines, neural networks, I don't know, Bayesian methods, tree-based models. This can be actually automated in a few lines of code. Like you use scikit-learn. Who of you uses scikit-learn sometimes? So many positive reactions. Scikit-learn does not offer much about neural networks, actually quite limited because they said neural networks is a totally different field, so they don't want to cover it much. But for everything that is available in scikit-learn, and there are probably hundreds of classifiers in there, you just don't know which one to pick. And you can do all this trial and error. You try a logistic regression, a Bayesian model, tree-based model, and you optimize all of these hyperparameters. It's still a lot of code, and you just don't know which one to pick. But you can say, hey, AutoML, concretely AutoSKLearn, do that work for me. Say, I want a classifier. I don't care about which one, but simply the one that works very well. So I say autosklearn.classification.autosklearn classifier, and I fit it to my training data. And once it found a good classifier, I can use it for prediction. Whether it's a Gaussian process, a support vector machine, whatever, doesn't matter. This will not obviously give me a perfect solution, and probably a machine learning expert spending a lot of time on this can do better. But a lot of the things you're learning in a machine learning class can be automated just in a few lines of code. So you need to think about how you can address this as a machine learning expert, how you can be better than that library. What you could do is you could maybe get the output, the model that was proposed here, and try to improve it further. Something like this. For this, you need the machine learning skills then. And you obviously need to know about your data pre-processing and so forth. But by such libraries, they already do some pre-processing, like how to scale your data and this kind of stuff. And so actually, this is a lot of the content taught in a machine learning class. So you need to think about what's your advantage, what you can offer on top, what these libraries don't do. And as this exists for scikit-learn, it also exists for Keras. And there are similar libraries for PyTorch, whatever. For example, for Keras, it's AutoKeras. So Keras is our our neural network library, and we can say, well, what I want is an image classifier. I don't care how many convolutions and how many layers it has and whatever. I just want an image classifier. Find me one for my training data that works well. This may take a little bit of time to run, but eventually I'll get an output. And that output is maybe quite good. And so I don't maybe need to worry too much about the exact number of layers and hyperparameters. Maybe the library can find me using machine learning and not just random trial and error, can find me something quite well. There is another joke about how to do the model selection. So model selection means finding the hyperparameters. There are other approaches to model selection. One joke is graduate student optimization. So a graduate student in American English means a student doing PhD studies and working towards a doctorate. And quite a lot of PhD students spend most of their PhD just finding a new model for some training problem. So by finding maybe some new architecture of the neural network, whatever, and they spend 3 to 5 years on this, and you put a lot of PhD students on such problems, and what you're doing is graduate student optimization. So it's a bit like a joke, but a lot of machine learning PhD theses look like that. Now, why are these libraries so popular nowadays? Like Keras and PyTorch, because training a neural network is quite resource heavy. And what you can do is, typically you cannot just run this on your CPU, but rather you need to run this on some different hardware to speed up the training. When you describe the tasks in a neural network, so like predicting or training, you can try to describe this in a vectorized way. Vectorized way means that you largely think in terms of matrices and vectors. Something we've seen before with our gradient descent. And if you're able to express your operations in a lot of vector and matrix operations, rather than in a lot of loops and working on scalar values, then this can often be mapped on a GPU. A GPU is a graphics processing unit that was initially used for playing video games, and rendering or actions in a video game for the rendering can typically be described as matrix operations or linear algebra operations in general, that you multiply matrices and vectors to move objects around. And if you do that, you do this on a GPU because a GPU is made for this. Modern GPUs have thousands of cores, and each core does very simple operations, like adding or multiplying scalar values. And was discovered also a bit more than maybe 10 to 15 years ago that you can describe the operations in a neural network in terms of matrix and vector operations. And then you can run this on a GPU. You still need CPUs because CPUs are very helpful for a lot of different computational problems. CPUs can even allow you to speed up very poorly written code because CPUs offer lots of features like branch prediction and out of order execution. These are some things we discuss in my big data course that is in the 6th semester. But CPUs have only limited parallelism. Maybe some cores, some pipelines, some things like SIMD, which is single instruction, multiple data, but a CPU doesn't have much parallelism. And GPUs, they have a lot of parallelism. The only problem is we need to be able to use them. So writing code for a GPU is tricky because we need to learn CUDA for NVIDIA or some other library for other GPU vendors. So we maybe don't want to learn how to write code for a GPU, and then the GPU is also not able to optimize it very well for us. So this would take quite some time to learn. And that's why libraries like TensorFlow, but also Lasagna already, or PyTorch or Keras, you write code in Python, and eventually this is mapped by the library on a GPU. So all the stuff we need, like backpropagation, or specifically the automatic differentiation, all of this is moved to the GPU as much as possible. This is a figure that appeared with the TensorFlow publication 10 years ago when TensorFlow came out. They showed, well, we needed GPUs to essentially just calculate these gradients, the partial derivatives, for lots of data, for very complex models. So we need automatic differentiation to calculate this for us. And we run this on a GPU, and we don't need to worry about writing code for the GPU. Rather, that code is generated by a library like TensorFlow, like PyTorch, whatever. And all we feed to the CPU are eventually these gradients, and we update our parameters and then use the GPUs again in order to calculate for the next round in our optimization algorithm, the gradients. And we can even use multiple GPUs with these libraries. So this leads to massive speed ups on GPUs. And if you need GPUs for your projects, say some of you will definitely do deep learning projects. If you need GPUs, we have these small GPUs that come with the robots, the NVIDIA Jetsons. But you already met Mr. Runkle, where you picked the robots. He also has very large GPUs available. There are workstations, servers, and all of this. So if you need that hardware, it's available for you, and you would just get in touch with Mr. Runkle if you need more computational resources once you're starting your projects. You can obviously also try to get free credit with some of the cloud vendors because they offer sometimes free credit for students to get to know their infrastructure. Feel free to look into that as well. But if you need to use GPUs, get in touch with Mr. Runkle, and he'll be most happy to make the hardware from the deep learning lab available to you. You can use also clouds, you can use tensor processing units. Tensor processing units are even more specialized than GPUs specifically for tensors. What is a tensor? Both a vector and a matrix are tensors, but tensors are more dimensions then. So with the vector, we have one dimension. With a matrix, we have two dimensions. We can have three dimensions, whatever. And it turns out some of these operations in a neural network can be expressed in higher level tensor operations. You can run this on a GPU, or you can even run it more efficiently on tensor processing units. That's also something that has become popular over the time. And that's why if you look at the NVIDIA website, they also offer tensor cores and this kind of stuff. It just means it's structure or hardware that is not constrained to 2D operations, but to higher dimensional operations that can be run efficiently. Or you can use something like FPGAs, which is customizable hardware that you could customize. So FPGAs are field programmable gate arrays, very generic flash cells in a chip that you can route in a different way for your specific task. And you could use this for also training your neural networks. But in this course, use the cloud or get in touch with Mr. Runkle if you need computational resources. Now comes one challenge. We've talked about that finding a neural network architecture is tricky. We can do trial and error, we can use grid search, we can use AutoML, but maybe there are already architectures that are quite helpful that we can reuse. And if you train a neural network from scratch, you need quite a lot of data and a lot of computational resources if the neural network is big and your data set is big. Maybe there are some best practice architectures we can use. And these are architectures proposed by others that prove to be helpful, and they offer them maybe not just as a paper or code, but even pre-trained. So pre-trained on a lot of data. And you can use these models either as is, or you can fine-tune them on your own data. So you would use the pre-trained model and fine-tune them. That's also something we sometimes call transfer learning, that you would have this pre-trained model and you would transfer it to a somewhat different task. And I just want to show you some best practice architectures that have historically been shared for neural networks. One of the early ones that became super popular 13 years ago is the AlexNet, which was an inspiration for a lot of people in AI. At that time, it was a neural network with 650,000 neurons, small from today's perspective. 650,000 neurons, and that means 60 million parameters, some type of convolutional neural network, and it performed well on the ImageNet dataset. So the ImageNet dataset in that time, the 2010 version, was 1.2 million images from 1,000 classes, and your goal was to classify the image correctly. So just classifying the whole image. And this AlexNet achieved a top 5 test error of 15.3%. Test error means on the test data that was not used for training, and top 5 means that you are proposing or that you are predicting your top 5 classes. So you take the top 5 output units, the ones with the largest value when predicting, and say, I'm predicting it's in one of these 5 classes. And if the actual class, the actual ground truth, is in that top 5, you would say you've done it well. So the top 5 test error was 15.3% with the AlexNet of that time. And on the ImageNet dataset from that time, 1.2 million images, 1,000 classes. Over time, better models were proposed as well as better data sets. And this is the AlexNet that was proposed. And what you also see here is you have the image and you have the convolutions that you would work on. And then you have pooling after the convolutions. You have convolutions again. So you have a few steps of convolutions and poolings. And eventually, this is all the feature detector. And here you would have 2 layers of hidden units. And eventually you have 1,000 output units for your predictions. So the actual learning of the task is this one here. And you have this as the feature detector. And now if you take the AlexNet and you want to customize it to a new problem, to a new data set, maybe you don't need to touch the feature detectors at all because they recognize features very well. Maybe in your training, you just need to touch the downstream task because you want to predict something different, maybe for a different number of classes, but you can use the feature detector as is, and you just need to do the training on here. This will be much cheaper and much faster and possibly much better than building the whole thing from scratch. If you use totally different data that have different features, maybe you also need to fine-tune the feature detector, but not necessarily, depends on your task. So also for your projects, you're most welcome to use pre-trained models and fine-tune them and customize them for your tasks. You don't always need to build a new network from scratch. You can, but it will be more challenging. You need more data, more resources, and so forth. So the AlexNet was the beginning of a huge series of neural networks that became popular. A few years later, the ResNet was proposed. And what it does is it proposes a new architecture that we will see soon there were different variations of the ResNet, one with up to 152 layers, and that network just 4 years later had an error of 3.57%, a test error on ImageNet, top 5 test error. So before it was, as you saw, 15%, and just 4 years later, less than a fourth. So dramatic progress in a short amount of time. What is a residual network? The ResNet means you're changing the structure, that it's not just one layer connected to the next layer. This is also the case up here. But what it proposes is that some information also sometimes skips 2 layers and then is fed into a layer after 2 layers again, as well as the actual information coming from the layer before. And these are residual connections, and this proved to be also quite effective when building neural networks. And this is all the feature detector, as you see. And eventually, we're just mapping to the 1000 output units. Probably there is a dense neural network as well. Yeah, we can see this also down here. There are 2 hidden layers with 4096 units that we need before mapping to the 1000 output units. So this is the residual neural network that was proposed. And one neural network that has become very popular over the years is YOLO. YOLO stands for you only look once. And what it does is it not only does classification of a whole image, but it actually does detection. So localization and classification. So it can locate an entity here, it can locate an entity there, and then it can actually classify these entities. Like we see there's a dog here, a bicycle there. And YOLO so this was YOLO version 4 from 2020. And since then, lots of new versions of YOLO have appeared. Just recently, the version 12 appeared. There was a paper about this just very recently when I prepared this course in March, with an ever better version of YOLO. And the good thing is these YOLO versions, they are available as pre-trained models typically. So you can download them from GitHub and you can use them for your problems. Maybe you fine-tune them, maybe not. And the good thing is it's all available for you. Just use it. And you can use this as a foundation for one of your projects. So obviously a project that would not be possible for this course is you just use a pre-trained model and you visualize some outputs and you're done. It doesn't work this way. But every year, quite some students use YOLO for some more sophisticated problem that they maybe customize YOLO, fine-tune it, and combine it with some other algorithms to do something. There is also smaller versions of YOLO, like one that fits on a mobile device or one of our robots. So there are lots of variations of these YOLO versions, and some students use them every year and customize them to their own problems. So you don't need to start from scratch and build everything from scratch. Feel free to use some work and build on top something new, but it obviously needs to be sufficiently complex and address that you would be working half the term on your project and you know how many credits this course carries and how much time is expected for this course. If you want to learn more about deep learning and convolutional neural networks, there's lots of resources available. There are obviously courses like Coursera, Udacity. NVIDIA offers plenty of courses that you can look up at their Deep Learning Institute. So this is not an advertisement for NVIDIA, yet a lot of hardware we use in our labs is from NVIDIA. And they offer really good courses, they offer certifications, but there are obviously other vendors as well. So I'm not just here speaking in favor of NVIDIA, but they're simply the leading company in this field, and they offer also really good courses if you want to understand more, like how you can do time series analysis with neural networks and so forth. So what we have done today is we have looked into object recognition, started with templates and histograms, then looked into machine learning and saw, well, for a traditional machine learning algorithm, we need to put in features because we cannot put in our raw images, which are just pixel values, but rather we need these feature detectors, but we don't know which ones to pick, and maybe we pick the wrong ones. And so ideally, we use neural networks that tend to learn features on their own. So we looked into neural networks, how they work, how they can be optimized. And then we saw how they can be customized to images using convolutions and pooling, or sometimes called subsampling. And we looked specifically then also in hyperparameters, automated machine learning, how to train it more efficiently on GPUs, for example. And we saw best practice architectures such as the ones here before, like YOLO. And AlexNet led to a huge popularization of computer vision. And just within a few years, these errors have gone down rapidly on ever larger and ever more complex data sets. And next week, we will also have a lecture. I sent you this and I learned already. Officially, next week, Thursday, is a lecture-free day because of the upcoming Easter vacation. But we are doing the lecture as usual, and it will be recorded in case someone isn't able to join. Um, I'm doing that lecture on a day that is officially lecture free because in a few weeks in May, I will most likely be away for a whole week on a business trip. And I also want you to advance quicker so you have more time for your projects. So if you can join live next week, I'd be most happy. And if you cannot, there will be the recording available as usual. And next week, we will continue with something quite interesting. So in terms of the foundations of computer vision, we have already progressed a lot. We looked at pixels, filters, segmentation, region of images, features, how to recognize objects, and in particular, convolutional neural networks. And all of this is important. But we've reached now the end of the foundations. And we can build now even high-level vision systems that recognize very complex stuff in images. Because you remember, we started with this hierarchy of vision tasks, low level, mid level, and high level. And we've reached high level now with object recognition and convolutional neural networks. If you take some computer vision courses, professors may only teach convolutional neural networks now and fully focus on them. I don't think this is the right thing to do because convolutional neural networks, they are helpful, but they're also not a silver bullet. For some problems, they don't work well. For some problems, you need proper pre-processing, like using the right filters, or maybe for some tasks that are controlled, you can find the features much more efficiently, or maybe you have a very limited amount of data, then convolutional networks are challenging. So convolutional neural networks are one of many possible solutions to your vision problems. And that's why we've discussed more in this course than just convolutional neural networks. But so far, it's all static. It's just images. And next week, we will look at image sequences. We will look at image sequences because you may have a video stream and things are moving in that video stream throughout the individual images. And we will look at motion in images. We will look at how we can track something in image sequences. And for this, we will look then in detail into temporal models and the Kalman filter. You may be wondering, what about recurrent neural networks? I'll talk about this next week. It's a different solution to these problems, but recurrent neural networks are something that would be discussed in Professor Wahl's deep learning course. But we will see why this Kalman filter is actually quite interesting also to vision problems. This next week will be lots of mathematics, so it will not be easy, but I will present it as understandable as possible with examples. Yet you should do a quick revision of something I will show you in a moment. And once we have finished this next week, we will also look at the optical flow and the correspondence problem. You should revise something for next week. I know this will be lots of maths, but I'm just looking for it. The Bayes rule. Who of you feels okay with the Bayes rule? Maybe just green sticker, thumbs up. If it's something you've definitely seen in your statistics course, maybe a red sticker if you don't feel comfortable with it. You will need it next week, and it's something that is definitely taught in the statistics course that you have already taken. If you don't feel comfortable with it or need a revision, please do so. Next week, I will assume that you know conditional probabilities, and we will just look into Bayes' rule very, very briefly, because it will be a foundation for all the other things we're doing, because we will look at temporal models. So we will look at temporal data, and the beauty of these models is they are highly generic. They not only work for vision data, but they work for a huge number of signal processing tasks. And we can customize them to vision as well. So it will be quite a lot of maths next week. So make sure you're fine with Bayes rule or Bayes theorem, whatever you call it. And next week probably will commit all the time on the image sequence processing. If there are any questions, I'm still here, but just indicate me if you have a question. If you have no question, maybe just green reaction that you're all fine, or red one if I shall wait. And with there not being any further questions, I wish you a great afternoon and spend enough time on the revision, as well as take a look at the TensorFlow playground for a better understanding of neural networks. Take care. Bye-bye.